It will acquire the minimum surface area and also it will have the elastic nature. So, elastic nature is there means, for example, let us take the spring. Spring is having the elastic nature, it can extend and then it can compress. If you take any normal thin wire, even it can compress and it can go back by the Hooke's law. Already we know that. You know Hooke's law, what we state? Hooke's law nothing but stress is directly proportional to strain. Up to the elastic limit, what happens? Nothing but the wire will have the elastic behavior. It can go back to the original position again. So, here in the same way, water surface also, by using the surface tension property, it will acquire the minimum surface area. Already yesterday I said that. So, only we will get the water in terms of drops. So, whenever you take the small amount of water, it will acquire the minimum surface area. Nothing but it will form as a drop. So, by the surface tension, it will acquire the minimum surface area, and also due to this, it will have the elastic nature. It will have the elastic nature, so only it will act like what? Stretched elastic membrane. So, it is stretching. Whenever you, for example, yesterday I have shown you that how the insect can stand on the water. For example, insect is standing and then water level is going down little bit. Now, whenever the insect is moving from there, then what happens? It will be there like that only, otherwise it will come back. It will come back. Nothing but whenever the insect is applying force on that, then what happening? It is going inside. Nothing but what happening here? Stretching. Whenever it is stretching and then whenever the insect is going away, at that time immediately it is coming back means it is storing which energy there? Elastic potential energy. That potential energy we known as what? Surface energy. Clear? So, here whenever the water surface is there like this, flat surface is there, whenever the insect is going, at that time it will become like this. It was flat first of all, normal water surface. Now, whenever the insect is going, at that time it is bending like this. Whenever the insect is coming out, at that time it will come like this. Nothing but what? Whenever the insect is applying the force, at that time it is storing the energy. That energy will be in the form of what? Potential energy, and then that potential energy is the here what is called surface energy, and also that surface energy will have to do little bit more for that. Now, whenever the insect is standing on the surface of the water, then it is going down means its area is increasing here. Stretching means obviously length increases. Length increases means what? Area also increases. So, whenever you take water will try to, what I said, water will try to have the minimum surface area. But what we are doing in stretching, we are working against the area to increase the area. We are working against the surface tension to increase the area. So, the best example is soap film. Whenever I have taken a rectangular section like this, a rectangular portion like this, and on that a movable wire is there. Rectangular vessel like a frame is there here, and that a movable frame is there. What I am doing? Nothing but I can move that frame, that wire like this and then like this. Nothing but I can increase the rectangle, I can decrease the rectangle. You are able to assume that what I am saying. So, here let us consider I have just a frame kind of thing like this. Now, on that a movable wire is there like this. Now, what I am doing? Nothing but I am just moving this one inside and then outside. I can move it inside or outside. This is movable. Now, in that what I am doing? Nothing but whenever it is there near, at that time I am just pouring some soap solution there. Whenever I pour the soap solution, soap film will have how many free surfaces? Two free surfaces. One is in, another is out. Soap bubble if you take. Even soap film also, bottom also free only, top also free only. Okay, that you have to remember. Nothing but soap film you cannot take on the water, right? Can you take soap film on the water? You cannot take that. Nothing but always you have to take in the air only. Air, nothing but air is touching how many surfaces? That surface and then this surface. So, how many surfaces? Two surfaces. Soap film or soap bubble, anything, you always remember that two surfaces will be there, free surfaces. Now, what I am doing means, I am just taking it near. At that time, I am just pouring some soap water on this and then I am moving away. Then what happens? What will be formed there? Soap film will be formed, right? Soap layer will be formed. Layer is nothing but film here. So, soap layer will be formed on that. Now, whenever I stretch more and more, and then at that some point of time I left it. I left it means, again what it will do? Up to some extent it is not yet blasted. I did not gone to the last limit. Up to some limit I have gone and then I left it. Then what happens? It will come back right again. Why it will come back? What is the reason? That is a surface tension property. Surface tension, what surface tension will do? It will try to have the minimum surface area. Now I am increasing the surface area here. Clear? Whenever I increase the surface area, obviously soap is also water only, liquid only. It will also will have the what surface tension property only. Whenever I increase the area, always due to the surface tension, what it will do? It will try to decrease its area. Now what happens means, obviously it will go back in this direction and then it will stop up to some limit. Nothing but here this is the equilibrium position. This is the normal equilibrium size of the soap film. Then what I am doing, nothing but from here I just pulled it like this and then I left. Then what happens, immediately it will come back here and then it will stop there. If I pull little bit more also, it will come back here and then it will stop. So whenever I am pulling it, whenever I am pulling this one, then what I am overcoming? Surface tension. I am overcoming the surface tension. Surface tension, and also I am making a displacement x here. Whenever you are applying the force and making the displacement means what you are doing there? We are doing the work. By applying the force, I am doing this much of displacement here. I am making this much of displacement. Then what I can say, nothing but I am doing some work against the surface tension. Clear? Why? Because surface tension, what it is doing? It is try to possess the minimum surface area. But what I am doing? I am doing against that one. I am pulling in this direction. But this wire, whatever the wire is there, that is trying to go that side. But what I am doing? I want to increase the surface area, so only I am pulling in this direction. Nothing but I am working against the surface tension. I am working to increase the surface area. Then surface area increasing or not? Increasing. So the surface energy formula is nothing but, the surface area formula is work done to increase the area and also the increase in area. To increase the area, how much work you are doing? That divided by how much area is increased. Clear? For example, initially the wire was there here. Initially wire was there here. It is the equilibrium position. If I leave the wire here, it will not go back and then it will not even come that side also. That is the equilibrium size of the soap film, whatever I have taken. Now, this is the initial area, let us take A. Now what I am doing, nothing but here whenever I pull it, at that time what it will do? What it will do, its area will be increases and it will also store some energy. Why? Because it wanted to go back. You just assume like a spring only. For the spring, it is the equilibrium position. From that equilibrium position, what I am doing, nothing but I am stretching it by applying the force. Whenever I stretch it, it will make the displacement. By that displacement, what it will do? It will store the elastic potential energy. Whenever I leave it, then what happens means it will go back again. It will go back to the equilibrium position. So here I am doing some work against the surface tension. Here in the spring restoring force will be there. In this that restoring force is due to which property, nothing but surface tension only. By the surface tension only, it will have the minimum surface area. Minimum surface area, nothing but it is going back. Going back, nothing but which force? That is restoring force only. So here by the restoring force, it will go back. But what I am doing, nothing but I am applying the force in this direction to increase the area. How much I increased here? X I increased. Whenever I increase the length to x, then area also increases. Area, how much it is increasing? Nothing but A dash, let us consider. Now whenever I am applying the force F here, I am increasing the length here, so that my work is equal to how much? Nothing but force into the displacement. And also the potential energy or surface energy here is equals to what? Nothing but the work done, this work done divided by this increase in area, change in the area. That is how much here? A dash minus A. A dash is the final area, A is the initial area, then change in the area, nothing but what you have to take? A dash minus A. That is the surface energy. You understand it clearly? So surface energy, nothing but by this energy, nothing same like the elastic potential energy only in the spring case. So by this energy, what it will do? Nothing but it will go back to the equilibrium state again. That's it. So that will be easily done by the soap film. So what I am doing, nothing but I am touching this one. Let us consider I have taken this is a rectangular shape thing. I have taken frame. Now what I am doing, nothing but a movable wire is there on that. Now first of all, what I did, nothing but I have taken this wire till here and then on this I pour some soap solution. Then what happened means I am just doing like this. I am just pulling it like this. At that time, in between them, what will be formed? Soap film will be formed, right? Soap layer will be formed. Now for that soap layer, let me take, this is the equilibrium state. This is the equilibrium state. Nothing but whenever I leave the wire here, it will neither go back and then nor come here. So it is in the equilibrium position. After that, what I am doing, nothing but I am just pulling it in this direction, little bit slowly, very slowly. If you do fast means it will get blasted. Now slowly I am just doing like this. At that time what happens, nothing but area will increases obviously. Whenever I leave it, immediately it will go back. Why? Because equilibrium state it wanted to acquire always. So due to which concept that is going back? Surface tension. What surface tension will do? It will give the minimum surface area for the surface, correct? So that by that property it is going back again. But whenever it is going back by the surface tension, again I wanted to increase area means I have to work against that restoring force. Restoring force is due to which property here? Surface tension. I have to do work against that. Now here I am making a x displacement. Already some area, already length is there L. On that I am just making x displacement here. Now whenever I make x displacement, at that time what will do, nothing but here at that time it will store some energy. That energy is the surface energy. Now for moving from here to here I am doing some work. That work divided by how much area is increased here. Initially only small area was there, now it is bigger area. How much area is increased? Clear? That is about the surface energy. Surface energy nothing but the work done to increase the area divided by increase in area, otherwise change in area. Clear? The work done to increase, I am doing some work, that work done divided by area you have to take. And also there will be a proof that surface energy is equals to surface tension. We will prove that, but you write the definition first. Surface energy. By the property surface tension, always liquid surface will try to acquire minimum surface area to increase the surface area we have to do some work against the restoring force. This restoring force is due to surface tension. This restoring force is due to surface tension. Then write the formula. Surface energy is equals to work done in increase in area divided by increase in area. Now here we will prove that the relation between the surface energy and then surface tension. Write that relation between surface energy and surface tension. That formula is very, very important. We are going to use in all the applications. Whatever the surface energy formula I said, very, very important. Relation between surface energy and surface tension. First of all, we will find out the restoring force here. Restoring force is due to which property? Surface tension property here. Now that surface tension is equals to, what is surface tension? S is equals to, what is the formula generally for us? S is equals to force by length. Correct? Force by length nothing but, force is here restoring force which one? F dash. F dash divided by how much is there? Length. L is the length, right? Initially the surface tension of this soap film is how much? Nothing but that is length is how much? L. How many free surfaces? 2 free surfaces. So that only what I can take, nothing but that is 2L. In the yesterday you don't confuse that again, she has to take 4L. Now why she has taken only 2L? Don't confuse that. Why? Because yesterday I kept this frame like this on the water. From that I am lifting. You understand? Now I just kept the film in the air only. In that air, in how many sides air is touching? Nothing but first one this side and then this side. In yesterday what we have done? Nothing but we have lifted the rectangular frame like this. At that time, on that what we have done? Nothing but on how many lengths the water is coming out. That is what we find yesterday. Don't confuse between that and then this. Yesterday we have found that like this. Let me take this rectangular frame I have taken exactly. Whenever I lift out from the water, whenever I am lifting out from the water, on how many surfaces water will try to come along with that? 1, 2, 3, 4. That is about the rectangular plate. If the film nothing but again 1, 2, 3, 4 inside and then outside. So that only we got how much? Nothing but if that is a square means that is L and all we have taken, 4L plus 4L we have taken. Let us consider square only. So in the same way here what I am wearing? Nothing but I am not taking on the water. Film you cannot take on the water. Whenever you go on to the water, then what happens? It will get busted, right? And then now I am taking the film like this. Now for this film, in how many sides air is touching? Nothing but one is for this surface, another is for this surface. Clear, you understand, right? So only here S is equals surface tension F, S is equals to restoring force divided by 2L. Here applied force is F and then restoring force is F dash. However, applied force is equals to restoring force but in opposite direction. In case of spring if you see, whenever I apply the force in this direction, then in which direction restoring force will be there? Opposite direction. That's it, opposite direction F dash. We will write this as a spring force. Fs is equals to what we will get? Kx minus Kx. And we are applying the force in opposite direction. So external force is equals to just plus Kx it will be. That's it. Okay. Now the restoring force S is equals to surface tension is equals to restoring force by the length of the soap film. So length, how many free lengths will be there? Nothing but 2 free lengths are there. One is this side, another is this side. So that F by 2L, then F dash is equals to how much I can write? S into 2L. This restoring force is equals to what I said? Applied force F into S into 2L. Now I have to do the work done. So work done is equals to, what is the work done formula for us? Work done is equals to force into displacement. How much force you are applying here? F force. How much extra displacement you are doing? X is the displacement. Very smaller. Very smaller. For the diagrammatic purpose I have shown like this. But that will be dx only. Very smaller. So here W is equals to force into the displacement X. F into X. Now this is a work done I got. Now my increase in surface area is how much? This F is equals to how much however? S into 2L into X. Okay, area is how much? L into X only. L and then X only. And after that you got how much here? 2 surfaces, so only you got 2L. A into B only, na? Area is equals to. Then here 2 into SLX. This is the work done we got. Then after that what you have to find out? Surface energy. Are you able to see this color? Shall I write with black otherwise? For reflection you cannot see the green. What is the reason? ಏನು ಸೈಟ್ ಪ್ರಾಬ್ಲಮಾ? ಕಲರ್ ಬ್ಲೈಂಡ್ನೆಸ್ಸಾ? ಯಾರಿಗಿದೆ ಅದು? This will have the wavelength, less wavelength, and then red and then black will have more wavelength, obviously. That purpose only. Then work done, surface energy, what is the formula I said? Work done by increase in area. Increase in area nothing but here, whenever you see after that how much area we have increased here. This is the, even then this is L means this is also L only. First of all square we have taken, after that we are increasing to rectangular. Now this is X and then this is L here. So that how much increase in area is? L into X. L into X. How many free surfaces again? 2 free surfaces, so only 2 into L into X. Then surface energy is equals to, I am sorry, this is a increase in area, right? 2 into L into X. Work done is equals to 2SLX. Then everything gets cancelled here. Then what is there? Surface energy is equals to surface tension. That is the proof. Let me explain again. So here what I am doing nothing but first of all I have taken the rectangular frame only. On that whenever I move the wire as a square, at that time each side is how much is there? L only there. Now first of all you have to find out the surface tension. First and foremost you have to find out the surface tension. Why? Because the restoring force is coming due to which one? Nothing but surface tension only. So that surface tension, to find out that surface tension, S is equals to force by length only. Here how many free lengths are there? 2 free lengths are there, 2 free surfaces. This is one length, the back side is another length. So that F dash divided by 2L we got here. Then F dash is equals to how much? S into 2L. What is F dash here? Restoring force due to the surface tension. That is equals to applied force obviously. So that applied force is equals to F is equals to also S into 2L only. Now work done I have to find out. I am doing the work to increase the length, how much? Nothing but X length. So only we got force into the displacement. Force is, what is the force we got? S into 2L into how much displacement I am making here? X displacement. So only 2SLX. That is the work done we got. Then surface energy formula just before what I said? Work done to increase the area divided by increase in area. So work done to increase area is how much? 2SL into X. That divided by increase in area you have to find out. Whenever you see the increase in area, only change in area, not the total. I said only delta A. Delta A nothing but in that example formula what I write? A dash minus A. Nothing but only this much I am increasing. Area of that one will be how much here? Length into breadth only. Length is how much? Length is there? L. Breadth is how much? X. How many free surfaces? 2 free surfaces. So only we will take it as 2LX. So that 2LX. Then surface energy is equals to, I have written work done by change in the area. Then we got SE is equals to S. From this what I can say? Nothing but surface energy is exactly equals to surface tension. Clear? From that only we will get all the formulas. So next remaining whatever you might be heard about these problems, whenever the one bigger drop is split into n number of smaller drops, at that time what is the work required to do that? Otherwise what is the energy consumed? Whenever the smaller drops are coalesced to form the bigger drop, at that time what is the energy released? That and all, that problems are important. Clear? That we will do. Next applications those are only. Just write this one. Two surfaces, no? Right, in the side you just write, so film will have 2 surfaces. So film will have 2 free surfaces. ಆ ಚೇರ್ಸ್ ಇಲ್ಲಮ್ಮ, ಫೋಲ್ಡಿಂಗ್ ಚೇರ್ಸು ಹಾಕೋಬೋದಲ್ಲ, ಈ ಕಂಫರ್ಟಬಲ್ ಇರಲ್ಲ. We are sitting in the chairs, you just take the folding chairs. How much time you will sit like that only? Yen Chandru, you are okay? Something happened. Tenga bididena tala mele. Kahan gaya Bahubali? Where is Bahubali? Bahubali? Bahubali 3 na shooting ಹೋಗಿದ್ರಾ? ದೇವಸೇನಕ್ಕೋಸ್ಕರ ಹೋಗಿದ್ರಾ? ನಾನು ದೇವಸೇನ ಅಂದೆ, ಉದಯ್ಗೆ ಅವ್ರ ಶ್ರೀವಲ್ಲಿ ನೆನಪು ಬಂದಿದ್ರು. ಡನ್, ಫಿನಿಶ್ಡ್. ಪಾಯ್ಸಲ್ ಈಕ್ವೇಷನ್ ಹೇಳ್ತೀನಿ ಅಂತ. Next, write a problem. Find the work done. Find the work done in forming. Find the work done in forming. You have to be fast. I will not stop for writing the notes, copying and all. Make a habit. Work done in forming a drop of radius r. Work done in forming a drop of radius r. So first of all, how to do that? Nothing but you know that surface energy is equals to surface tension we got. Correct? Surface tension nothing but S only. We will take surface energy is equal to surface tension. That is equal surface energy formula is what we got. What's the surface energy formula? W by delta A. Delta A nothing but initially it is not having any radius. Now you are forming that as a drop. Whenever you form as a drop, then change in the area is equal to how much? 4 pi r square minus 0. Initially 0 radius, initially 0 radius. Finally you are forming into a drop. Initially like this is there. Finally you are forming into the drop of radius r. Initial area is, there is no radius, so only we will not take it as a spherical, and then there is no area only. So finally you are taking the area is how much here? Spherical drop nothing but area is 4 pi r square. Surface area is 4 pi r square. Only sphere we will get here. Volume of the sphere and then surface area of the sphere you have to remember. That is 4 pi r square and then 4 by 3 pi r cube. Now this is the final area minus initial area. Now work done is equals to surface energy. I will not take surface tension only I will take. Why? Because I know the surface tension of water obviously. So that S is equals to W by delta A. This work done I have to find out, then S into delta A, that's it. Always work done nothing but S into delta A. Force nothing, this one force nothing but S into L. Correct? Surface tension formula is what? S is equals to F by L. F is equals to what I can say? SL. That is a F. Now work done nothing but S into A. Just remember like that. One is force nothing but the surface tension into the length. Work done nothing but surface tension into the area. That's it. Now surface tension is S here. Delta A is how much? Final area is 4 pi r square. That is a W. Finished. Write a note. Usually for the numericals, for the numericals, force is equals to, you write S into length you write in words. F is equals to S into length. In the next line exactly down of that, work done is equals to S into delta A, S into change in area, Clear? That is how you have to remember always. Force means S into L, work done means S into area, that's it. Now next problem. Find the work done in forming a soap bubble of radius r. How much? 8 S pi r square, that's it. Why? Because soap bubble will have how many free surfaces? 2 free surfaces. One is inner area, another is outer area, that's it. Whenever you see this one liquid drop, inside everything water will be there. Inside is not free. Liquid drop if I consider, inside not free. But if I take the soap bubble will have how many free surfaces? One is inside, another is outside. Now what is our work formula? Nothing but S into delta A. How many free surfaces? 2 free surfaces, so only 2S you have to take. Surface tension is 2S. That into delta A is how much, however? 4 pi r square. So your answer is 8 S pi r square. That is the work done in forming a soap bubble. Right there. Soap bubble will have 2 free surfaces. Then show water తీసుకురా banana. Soap bubble will have 2 free surfaces. Next problem. Find the work done in blowing a soap bubble of radius. Find the work done in blowing a soap bubble of radius R1 to R2.
Yes.
బాటిల్ లేదా? How much? 8 s pi r2 square minus r1 square. 8 pi s r2 square minus r1 square. Why? Because initially the soap bubble was there of how much radius? Nothing but r1 radius. Now finally whenever I blow it, at that time what happening means it is becoming as a soap bubble of radius how much? Nothing but r2 as a radius. Now you have to find out the work done. To find out the work done, what is the formula? Work done is equals to S into delta A. Here soap bubble means how many surfaces? 2 surfaces. So only 2s into delta A, final area minus initial area. So that 4 pi r2 square, this is the final area, minus 4 pi r1 square. Now what I can take common here? 2s 4 pi outside, then what is remaining? r2 square minus r1 square. That is the work done in blowing the soap bubble from radius r1 to r2. These are all important. All the applications whichever I said, these 3 problems are important. Next one also very very important. Next one you try by your own. After that I will explain. You try with pencils. If big water drop of radius capital R is split into n number of smaller droplets, then find the work done in doing so. You have to find out the work done. Very very important. Same concept, not the same problem, same concept. Again bigger drop into smaller drops, you will get in number of chapters. Do that properly. NS4 pi, no. No, you will not get the answer that much easily. N power 2 into? No, you have to do still. Your final answer should be this one. 4 pi r cube into 1 by r minus 1 by capital R. This is the work done. S into. That's the final answer. You have to find out everything. Change in the area you have to find out. Work done also. Work done nothing but you have to find out first of all change in area only. Find that. Or you can get S into 4 pi r square n power 1 by 3 minus 1 also. N power 1 by 3 minus 1, not 2 by 3. You got that? ఇది n power 2 by 3 क्या?
Small r, capital R is equal to n power 1 by 3 r square r. R. R power n power 1 by 3 2 by 3 r square minus r square n power 2 by 3 minus 1 r square.
Small r square common ತಗೊಂಡಿದ್ದೆ, capital R square ತಗೊಂಡಿದ್ದೆ ಅಂದರೆ n power 1 by 3 ಬರೋದು. Very good, very good. Done anybody? At least you have to get this answer. S into 4 pi capital R square into n power 1 by 3 minus 1. At least this one you have to get the answer. Yes, you got that? How many of you got? Raise your hands. 1, 2, 3. Good, very good. 4, 5. Good, good ma. See that, I will explain that. This concept is important and very easy also. You get the same concept in different chapters, so that you have to remember the process what you will do. So here I have said, first of all, a liquid drop is there of radius how much? Radius is capital R. Now this one I split it into n number of smaller droplets. N number of smaller droplets like this it is there. Of each of radius is how much? Small r. And then how many number of are there? N number. Whenever I mix all, at that time what I can do? Again I can form the bigger drop. Here you are saying that, you are only saying that whenever I split it, I am just forming the n number of droplets. Whenever I join them, I coalesce them, at that time what I can form? Bigger drop. So what you can say here? Shall I say that volume is constant? Volume is same. If you are mixing together all, at that time again I am forming this only. If I am splitting this one, again I am forming this one only. Nothing but what happening here? Volume is constant, volume is conserved. There is no wastage of water here. You are splitting into number of droplets and then you are joining, you are coalesced to the form the big drop. So always here volume remains constant. Why? Because density is same only, however. Water before also water, after also water only. So volume also same only here. So what I can say, nothing but V dash is equals to V. Final volume is equals to initial volume. You understand, right? How the volume will be same? Splitting into number of droplets, then again that water only, that much of water only. Again coalesce to form the big drop, again that much of water only. So volume is constant here, volume is conserved. So final volume is equals to initial volume. So final volume, finally how many droplets are there? N number of droplets. N number of droplets of each of volume is V, let us consider. Initial volume is bigger V. Now n number of smaller droplets, radius is how much here? Small r. So that what is the volume? 4 by 3 pi into small r cube. That is equals to bigger drop water radius is how much here? Capital R. That is how much? 4 by 3 pi capital R cube. Clear? Now here 4 by 3 pi gets cancelled. Then R cube is equals to clearly what I can write? N into small r cube. Now let us do divide by 3 both the sides. 1 by 3, 1 by 3, 1 by 3. Why? Because I want to cancel this 3 here. So the 3 gone, 3 gone. Then capital R is equals to what I can say? N power 1 by 3 into small r. That is a capital R value. You have to get this relation first. Then automatically you will get the answer, final answer. So here what I am doing, nothing but whenever I split this bigger drop into smaller droplets, the volume is always conserved. Final conserved, nothing but what I can say? Final value is equals to initial value only. So final volume is V dash, initial volume is V here. Final volume is due to how many droplets here? N number of droplets. So that N number of each droplet volume is small v I will consider. That is equals to bigger drop volume is capital V I will consider. Now here I am writing it as N into smaller volume is how much? Small droplet volume is 4 by 3 pi into what is the radius of that? Small r. So 4 by 3 pi into small r cube. That is equals to bigger drop radius is capital R. So only 4 by 3 pi into capital R cube. 4 by 3 pi gone. Then what is remaining here? Capital R cube is equals to N into small r cube. I want to cancel the 3. So that what I can do, nothing but I can divide by 3 both the sides powers. Then what is remaining for us? R is equals to N power 1 by 3 into small r. This relation is important. R is equals to N power 1 by 3 into small r. Now you have to find out the surface work, nothing but what is the formula for us? Work is equals to S into delta A. Surface tension into delta A. Then delta A is equals to what is the answer for us? Final area minus initial area. Finally, how many areas are there? N areas are there. Each area is how much? Nothing but of smaller radius R. So that N number of small areas, let me take small a minus capital A. Clear? So that N number of small a, area of each droplet is how much here? Droplet, again spherical shape only, 4 pi r square, 4 pi into small r square minus capital A, nothing but how much? 4 pi into capital R square. Now here what I can take common, nothing but 4 pi I can take common. Then what is remaining for us? N r square minus capital R square. Now in the place of capital R square what I can write? N power, capital R nothing but N power 1 by 3 into small r. Either you can convert entire equation into small r, otherwise entire equation into capital R. In general way, they will give always capital R value only. They will not give the small r value. So for that, here what I can write? Small r is equals to From this relation, yes, very good. Small r is equals to r into n power minus 1 by 3. Clear? Now, here 4 pi into n into, in the place of smaller what I can write, nothing but r into n power minus 1 by 3 whole square is there, whole square minus r square. Now 4 pi into what I can take common here, r square I can take common from here and then from here. Then what is remaining here, n into n power minus 2 by 3. Correct? Here n into and then n power, how much is there, whole square, square is there, minus 2 by 3. That minus r square already gone out, then how much is there, only 1 is there. Here n power 1 and then 1 minus 2 by 3 gives you how much, 3 minus 2 nothing but 1 by 3. So that 4 pi r square into n power 1 by 3 minus 1. That is the final change in the area, delta A only. Now you have to find out the work done. To find out the work done, what is the formula for us? S into delta A, that's it. So that the work done is equals to here, S into change in the area is how much? 4 pi r square into n power 1 by 3 minus 1. That is one form of the answer. You have to check the options always for this problem. And then another form of the answer, I don't want to get even n also. I want to get only capital R and then small r. Then what I can do? I have to remove the n from the formula, that's it. So to remove the n power 1 by 3 is equals to what I can write? Capital R by small r. So for that purpose, even here s into 4 pi r square, 4 pi capital R square into, in the place of n power 1 by 3 what I can write? Capital R divided by small r. So that r by r minus 1. From this again I will take r capital R outside here. So that what will be remaining there, s is equals to, see, work done is equals to s into 4 pi r cube, r is coming out already, 1 by r, here r is not there, so that what I can get, 1 by minus 1 by capital R. That is the answer, final answer. Clear? Even this is also answer only. Anything wrong in that? r by r only, right? Correct only. I will explain that. First of all, copy. Emma, Sana? Entire derivation is there only in this concept, that's it. If you know this one, everything you can do easily. See that always formulas are not useful for the problems, concept also useful only. You should know the concept first. If you don't know here how the volume is conserved, means you cannot get the answer there. And Manoju, here, so my relatives' names are there. Here, Manoj means my chikku mama or son, chikku uduga. Don't think so much. Chikku uduga, I think he is a second class or third class. And then Danshu, I'll call it as Danshu, right? Actually, my brother daughter's name is Danshu, Devanshi. And my Doddu mama or daughter name Deepika. So I'll call her Deepi like that. So many relatives are there. Srivalli ನಮಗೆ ಏನಾಗ್ತಾರೆ ಉದಯ್ ಸ್ಟೂಡೆಂಟ್ ಆಗ್ತಾರೆ. ಎಸ್, ವೆರಿ ಗುಡ್. ಒನ್ ಆಫ್ ದ ಸ್ಟೂಡೆಂಟ್, ಲಾಸ್ಟ್ ಕ್ರ್ಯಾಶ್ ಕೋರ್ಸ್ ಸ್ಟೂಡೆಂಟ್ ಶ್ರೀವಲ್ಲಿ. ಹೌದೌದು, ಯುವರಾಜ್ ಇದರ ಯಾರಣ್ಣ? No, they came for crash course, you know that. At that time, one Srivalli was there. And they were dancing always in the class whenever nobody is there. CC camera ಅಲ್ಲಿ ನೋಡಿದೀವಿ, ಹೌದು, ಕರೆಕ್ಟ್. ಇಲ್ಲ ಆ ಥರ ಸ್ಟೂಡೆಂಟ್ಸ್ಗೆ ತೋರಿಸಲ್ಲ ನಾವು. See that? Listen again. Listen this one. Now here, a bigger drop of water is there. Listen again, silence. So here bigger drop of water is there, that of radius is how much? R. Now I am just splitting into number of smaller droplets. So at that time what happens? Nothing but volume remains conserved, volume will not changes. So that this how many number of smaller droplets? Nothing but n number of droplets, each of radius is how much? Smaller. Actually what people will do, nothing but what is the most students will do the mistake means they will take 4 pi into n into r square, they will take here n square r square they will take, then they will get the wrong answer. That's wrong. Here what you will think, nothing but here capital R is equals to n into small r, like that you will think, and then you will find out the answer. That's wrong. Here area nothing but each area you have to take totally how many areas? Nothing but n number of areas are there. That is what how you have to do. Now here volume is conserved, nothing but final volume is equals to initial volume. Final volume is due to which one? Nothing but droplets. Initial volume is due to the bigger drop. So here n into n times of each volume you have to take. Correct? You should not take that 4 pi into n into smaller whole cube, you should not take. Clear? So that n times of each volume you have to consider. So that n into each volume is how much here? 4 by 3 pi into radius is how much? Small r cube. So that small r cube I have taken, that is equals to capital V, nothing but the volume of the bigger drop. How much that is? 4 by 3 pi into capital R cube. Now this 2 gets cancelled here, then what I am writing, nothing but r cube is equals to n into small r cube. Now I want to get only r. For that what I can do, nothing but I can divide both all the powers with 3. Then I have divided and then we got r is equals to n power 1 by 3 into small r. Now from this relation, however you want, you can write that small r is equals to how much it will be? Capital R into n power minus 1 by 3 as per the given problem. In the given problem, if they give the radius of the bigger drop, at that time you have to take the small r value and then you have to remove the small r from the answer. Whenever they have given radius of the smaller drop and then bigger drop is not given, at that time what you have to remove? Capital R you have to remove from the given answer, whatever the answer you got. So here capital R is equals to n power 1 by 3 into smaller. As per your requirement you have to do that. If n is not given, at that time you have to remove the n. Whatever is not given in the problem, you have to remove that. To remove that you have to substitute the other values, that's it. So here in this problem let me take capital R only given, small r is not given. At that time in my problem small r is there in the place of small r, again I have to write as capital R only, in terms of capital R only. So here capital R is equals to n power 1 by 3 into small r, then small r is equals to r into n power, obviously it will go that side, then n power how much? Minus 1 by 3 will be there. So here you have to find out the work done in forming that kind of droplets, means you have to do some work. So work is equals to what is the formula? Surface tension into area. Force is equals to what is the formula? Surface tension into length. Work is surface tension into area, force is surface tension into length, you have to remember. That length also, how many free surfaces are there you have to consider. Amma Nigerian, Kelramma class solpa. So here surface tension into area you have to take, change in the area by the way. Change in area means what? Final area minus initial area. Finally which area you have to consider? Area of the droplets and then initially area of the bigger drop. So that area of the small droplets. Area of droplets nothing but you should not take 4 pi into nr square. You have to take n times of each 4 pi r square. Clear? I am mentioning this many times, don't confuse in that again. So what if people will do, nothing but here directly 4 pi into nr whole square you will take. You should not do that. Why? Because n number of each droplets are there, so that n into each area how much? Nothing but smaller area minus capital area, a final minus a initial. Now here small a is 4 pi small r square, 4 pi capital R square. From that I have taken 4 pi outside. Even in the place of smaller what I can write, nothing but capital R into n power minus 1 by 3. So that I have written that only, but whole square is there here. So what I can do, nothing but here r square n power minus 2 by 3. From this r, from this one I have taken r square out. Then what is remaining? Nothing but this n as it is remaining into n power minus 2 by 3 is remaining here. N power minus 2 by 3. N power 1 minus 2 by 3 how much it will be? N power 1 by 3. So n power 1 by 3 minus 1 gone out. That is a change in the area. Now you have to find out the work done, nothing but surface tension is S and then change in the area is this one. Whenever they have given the capital R and then N. Whenever they have given they have not given the n, they have given capital R and then small r. At that time, in the place of n power 1 by 3, what I can write? Capital R by small r. That is what I have written here. So this one also correct only, but you want to get in term, still you want to do nothing but I can take here r also outside here, then 4 pi r cube into 1 by small r is there. Here nothing is there, nothing but 1 by capital R you will get. Clear? That is about the problem. You have to remember that properly. Work done in forming the number of droplets. Clear? For that extension problem. Find the change in the temperature for the above problem. Find the change in the temperature for the above problem. Find the change in the temperature in the above problem. In brackets, specific heat of water is small s. Specific heat of water is small s. Get that? First of all, tell me that generally what is the formula? Nothing but Q is equals to ms delta T. You have to take energy formula. Okay, that we will do later. First of all, whenever you are just forming the bigger drop into number of smaller drops, at that time what happens? First of all, tell me temperature decreases or increases? Nothing but you will feel more cold in the in the cold areas. Nothing but at that time what is there in the air? Nothing but smaller. For example, in the rain also, whenever you got the rain breeze, otherwise rain drops. Whenever you are getting the rain drops, at that time you will not feel cold. Whenever you got rain breeze, at that time you will feel cold. Clear? So here whenever you are splitting the bigger drops into number of smaller drops, you have to do some work. It is absorbing the energy there. It is absorbing the energy, nothing but the temperature will decreases. That is absorbing, otherwise releasing, you just forget about that. You just get this example only. Whenever rain is pouring on you, you will not feel that much cold. But whenever breeze is coming towards you, at that time you will feel more cold. In breeze, what happening there? What is coming in the breeze? Droplets, small droplets. In the rain, the big drops are pouring on you. Clear? So that here what happens means temperature will decreases. Just remember the concept. Temperature will decreases whenever bigger drop is forming into number of droplets. Now whatever the temperature is decreasing or increasing, it is changing however. So what is our work done formula? Nothing but the work done is equals to, what is the formula we got? Work is equals to S into 4 pi r cube into 1 by r minus 1 by capital R you got. Now this work done is equals to, can I say that work done is equals to energy? Work is equals to energy by the work energy theorem. And then here they are mentioning the temperature, nothing but which energy it will be? Heat energy. You have to take, always see that techniques are important. What given is important. By given problem only you have to think about the solution. Here work is nothing but energy only. That is which energy? Kinetic energy na, potential energy na, heat energy na. As per the given problem, heat, they have given temperature, nothing but heat energy. If they have given velocities, at that time which energy? Kinetic energy. If they have given height, at that time potential energy. Understand? As per the given problem only you have to think everything. So here they are talking about the temperature, nothing but our work done is nothing but that will be the heat energy. That is a Q. Q is equals to S into 4 pi r cube into 1 by r minus 1 by capital R. Q is equals to, what is the formula? Basic formula is ms delta T. Here specific heat they mentioned about the water, whatever they have given, so that m into s into delta T, otherwise delta temperature theta, that is equals, this s is nothing but what? Capital S. Capital S is what? Surface tension. This small s is what? Specific heat. So that capital S 4 pi r cube into 1 by r minus 1 by capital R. Did they mention any mass here? Mass of the water? Instead of mass what I can take? Density into volume. So that rho into volume we have to take first of all. Volume of the bigger drop is how much here? 4 by 3 pi into capital R cube into small s into delta theta is equals to s into 4 pi r cube into 1 by r minus 1 by capital R. Now here 4 pi gets cancelled, then r cube also gets cancelled, divide by 3 is there as it is. Now what I can write, nothing but delta theta is equals to, what we can write, delta theta is equals to 3 capital S, S will not get cancelled ma, by the way, remember that, just make that difference. So that 3 into S into, what is remaining here, 1 by small r minus capital R, that divided by, what is there here, rho into specific heat small s. Okay, this one you just make a difference, specific heat, that one is small s. Now here also in this one, this is which energy, nothing but mechanical energy. Here this one is what, heat energy. At that time how to do the conversion between them, mechanical energy into heat energy. What is that? What you can do, you have to multiply with what value, 4.2 joules, right? You have to convert always. You have to make that conversion in the final answer. Clear? In the numericals, whenever you are doing, at that time you have to apply that value. Why? Because here which energy we got, nothing but mechanical energy. Here this energy, which energy we are taking, heat energy. Heat energy will be in terms of calories only. You have to, obviously you have to convert into joules. Clear? That one is okay, but this one is the final answer. 3s by rho into s, 1 by small r minus 1 by capital R. That is the answer. Write that in this, capital S is surface tension and small s is specific heat of the water. Specific heat of the water. Next, one more problem you write. We'll collapse the droplets into bigger drop. Okay, now bigger drop to smaller droplets. Now smaller droplets to bigger drop. Directly we'll do the problem only. Numericals. Calculate the energy released. Calculate the energy released when 1000 small drops, when 1000 small drops, each of radius 10 power minus 7 meters, each of radius 10 power minus 7 meters, coalesce to form one large drop, in bracket, take the surface tension of water is 7 into 10 power minus 2 Newton per meter. 7 into 10 power minus 2 Newton per meter. Again apply the conservation of volume only. Then you will get the answer automatically. 7 into 10 power minus 2. Again volume conservation only. Same like this only, but you have to do in reverse. That's it. Everything you have to do. Don't write directly. Same procedure. This much time. Was answer good. 7.9 into 10 power minus 12 joules. At least change in area you got as 36 pi into 10 power minus 12. Change in area. Yes, you got it? The answer is 7.9 into 10 power minus 12. Yes, Vinutha, very good. Then, anybody else? Good, ma, good. At least change in area you got 36 pi into 10 power minus 12. 36 pi into 10 power minus 12. Then find out this work done, no? Surface tension given already. Multiply, that's it, you will get the answer. See that? Don't write directly this formula. This formula is wrong for that. You are doing the reverse operation. You are doing the reverse operation. This formula is wrong for that. So you have to do in reverse. This one to this one. Entirely you have to follow again the new procedure. But same procedure only. But you have to do newly. So here, whenever I have taken n number of smaller droplets are there. Each of radius, how much they said, small r is equals to 10 power minus 7 meters as they have given. So that is a r value. That is collapsed to form a bigger drop. Bigger drop of radius, how much? Capital R is there here. Bigger drop of capital R radius. Now, in that process, what you are doing, nothing but you are just remaining the volume change. Volume is same only. So that what I can say, nothing but final volume is equals to the initial volume. Final volume is how much here? 4 by 3 pi into capital R cube is equals to initial volume. How many number of droplets are there? N. N is how much they have given? 1000 number of droplets are there. Each of volume is how much? 4 by 3 pi into small r cube. This is what you have to do first. Now here 4 by 3 4 by 3 pi gone. Then r cube is equals to, can I write this as 10 cube? 1000 as 10 cube I can write. Then small r cube is there here. Then what I can cancel here? Everything cancel, cube cancel. Then capital R is equals to what I can write, nothing but 10 into small r. Smaller value is how much here? 10 power minus 7. So that how much you will get here? Minus 6 meters. Radius is a minus 6 meters. 10 power minus 6 meters. Then delta A. Yarama, Corona sister? 4 pi. N times of 4 pi small r square minus 4 pi capital R square. Final area minus initial area only. Final is how much? Final is capital R, na? Yes, reverse I have written. 4 pi capital R square minus n number of small drops are there. Each of area how much? Small r square. Now here 4 pi I can take common and then r square nothing but r value is how much here? 10 power minus 6. So that how much you will get? Minus 12 minus small n is how much? 10 cube. Small r is how much here? 10 power minus 7. 10 power minus 7 whole square nothing but 10 power minus 14. So here 4 pi into 10 power minus 12 minus this one is how much? 10 power minus 11. Minus 11. So this one is nothing but, can I take this one as 10 power, how much that is? 10 into 10 power minus 11, no? No, it cannot be. This one 10 into 10 power minus 12 I can take. So that 4 pi into, you are able to see this? I will write here. See that here delta A is equals to 4 pi into, how much is there? 10 power minus 12 is there. This one what I will do, nothing but I will write as 10 into, how much? 10 square will be there? 10 cube nothing but what I can write? 10 into 10 square. 10 into 10 square into already what is there here? 10 power minus 14 is there. Now 4 pi into 10 power minus 12 minus 10 into minus 14 plus 2 is how much? 10 power minus 12. 10 power minus 12. Now from this what I can take common? 10 power minus 12 I can take common. 4 pi into 10 power minus 12 is coming out. That into what is remaining? 1 minus 10. So that this 1 minus 10 gives you how much? 9. 9 4 is 36 into pi into 10 power minus 12. Here why we got minus? Nothing but here energy will be released. So only you will get the minus here. Why? Because temperature increases here. Clear? Smaller droplets are forming into bigger one, nothing but the temperature will be increases. So that what happens? Nothing but energy will get released. System is given the energy. So only minus you are getting. Don't confuse about that. Now this is the delta A. Then work done is equal to what is the formula for us? Tension into area. Tension is how much here they have given us? 7 into 10 power minus 2, and then change in the area is 36 pi into 10 power minus 12. So whenever you multiply everything, then what is the answer? You will get nothing but 7.2 into how much you are getting finally? 10 power minus 12. 792 now. Okay, this is the work done. First of all, listen again, once again last. So here we are forming the smaller drops into bigger drop. Smaller drops how many are there? N number of are there. However, you are forming the bigger to smaller or smaller to bigger. Always volume is remains constant. Volume remains constant, nothing but final volume is equals to initial volume here. V dash is equals to V. Now this final volume is 4 by 3 pi into capital R cube is equals to initial volume is how much? Nothing but each of having how much volume? 4 by 3 pi into small r cube. How many number of are there? N number of are there. So that only n into 4 by 3 pi into small r cube. Now everything I cancelled here. This 1000 I can write as what? 10 cube. For the easy calculation purpose I am doing like this. Again, whenever you take here r is equals to again n power 1 by 3 means you don't know how to take the 1 by 3. So every time they will give 27 or 64, 8 or 1000, nothing but cubes only. More than that nothing will be given. I am damn sure about this. Always they will give direct cubes only. Either 2 cube 8, 3 cube 27, 4 cube 64, or 5 cube 125. Like that only they will give. Clear? So here also, so only they have given 10 cube here. Always they will give like that only. Any value they have given means that is cube of something. First of all find out that cube value, how much that is. Now cubes got cancelled, and then here 10 into smaller value already mentioned in the problem, that is 10 power minus 7. So the 10 power minus 6 meters we got here. Then now you have to find out the change in area. Why? Because work done is equals to what is the formula? S into change in the area. So delta A is equals to final area minus initial area. Final area is how much? 4 pi into smaller capital R square minus initial area. Each area is how much here? 4 pi small r square. How many number are there? N number. So only n I have taken here. Now this calculation is important here. Now r square nothing but how much? 10 power minus 12 here minus n is 10 cube. Small r square nothing but 10 power minus 14 you will get. Why? Because 10 power minus 7 is there here. Now from this you have to take one letter as common, one number as common. For that purpose I will keep 10 power minus 12 as it is. This one I will write as 10 power minus 12. How to write that? Nothing but 10 cube I can write as what? 10 into 10 square. So that 10 into 10 square I have written into 10 power minus 14. 10 power minus 14, 10 square, how much it will be? 10 power minus 12. Here 10 power minus 12 is there, here also 10 power minus 12 is there. You can take it out. So but what is remaining here? Still 10 is remaining. So I have taken that out, and then 1 minus 10 is remaining here. 1 minus 10 nothing but minus 9 you will get. Why minus 9? We got nothing but energy is released by this work, and then temperature got increased. So only here minus we will get, you just leave about that. Delta A is equals to 36 pi into 10 power minus 12. Now again I have just multiplied with surface tension, that's it. Clear? Chalo.